This talk is about a very long 50-year history of the development of silicon chips that mimic somehow the eye, starting in Japan in 1970 and ending just last year, or actually this year, here at INI and also with the chip that was presented last year at the International Solid-State Circuits Conference from one of the big image sensor companies. So I try to take you on this intellectual and technical journey, hopefully within this time, and give you some taste of all the ideas that were floating around, the circuits that were tried, the ones that didn't work, why they didn't work, what things stayed around, and the fun that we had on this journey, because it was fun. It was just pure fun almost all the way. And so I hope I can share that journey with you. And it starts with this picture here of the horse in motion from Muybridge, who turned out to be a murderer. You can read about that. But this movie is one of the original movies ever shot. It's about 40 frames long, and it's now 50 years old, 150 years old. So this idea that you should represent video information, visual information as a sequence of snapshots has had real staying power, right? It's lasted for 150 years. That means it was a really good idea. And yet you can see now that it has drawbacks, that most of the pixels don't change. The scene barely fits the dynamic range of the film, and you get a lot of aliasing, right? And fundamentally, you have this problem with these cameras, but still the image sensor community doesn't think that there's a problem, because around 2010, Eric Fossum, who is one of the three godparents of modern CMOS image sensors, along with Nobuchi Nishi and Albert Wishin, he stood up at the International Image Sensor Workshop and defined the perfect image sensor. Do you know what it is? It has infinitely small pixels, infinite dynamic range, and infinite frame rate. Right? And that's what the image sensor world would like to produce. And of course, you know the drawback of that is that it has infinite data rate, infinite redundancy, and infinite power consumption. And fundamentally, what we discovered not too long ago, in fact, it took about a decade after the invention of the event camera that we realized that there was the problem with frame cameras is that they have a fundamental latency versus power trade-off. You can burn arbitrarily low power by just going at very low frame rate. But then, of course, you have to wait for the next frame to react, right? And if you want to get short reaction time, you have to run at a high frame rate, but that costs you more power. And all this is actually worked out quantitatively in this very nice IEEE Signal Processing Magazine article from us. It's quantitative power latency products that characterizes this. But we go back to the inspiration for all this is considering the human eye as a digital camera. And I'm sure you all know that there's 100 million photoreceptors here, coming out as 1 million output nerve fibers carrying spike rates of up to 100 hertz. The whole eye burns a few milliwatts, and it has many teraops of computing, and it actually has about 20 different representations of the visual world. And it operates over a dynamic range of about 1 billion, from starlight to bright sunlight. And so this is an inspiration that maybe you don't just have to send pictures. You can try to compute something more informative on the camera output. The question is, how do you actually do that? And so that actually goes back all the way to Kunihiko Fukushima, who was funded for many decades by NHK Research Lab, which is actually funded by the Japanese television corporation, the National Television Corporation. And he's famous for developing the neocognitron, which anticipated many of the things that appeared decades later in deep learning, like max pooling and CNNs and things like that. But the very first thing he did was an electronic model of the retina. It was built out of discrete components, 700 actual phototransistors, a board with 700 of these buffered amplifiers, and then these resistive sheets to mimic what was happening in the horizontal cell layers of the retina, the spatial temporal averaging that happens right behind the photoreceptors. And you can see what the output is. It's the difference between this average of the light intensity and this average over here. And then that's what's actually sent out through a bipolar transistor to activate a lamp, a physical lamp. And the whole thing occupied a cabinet like this. And this is the output display right here, these lamps. And you could show it a visual input. I don't know where the lens was, perhaps it was here. And if you showed it a flashing spot, you would get nothing at first, a white spot. then you'd see the flash, and then the surround would kick in, and you'd see only the edge of the spot. And so that was the very first electronic silicon retina. It's really a cool creation. Not practical for anything, but beautiful. About a decade later, I think Carver had just come off his synchronous logic journey with the publication of the Meade Conway book that started the whole Silicon Valley journey of synchronous logic design. And he became interested in computing in the nervous system. And then Misha Mahowald, a young biology student, came into his lab and she said, let's do a silicon retina. And so they decided to first design the silicon retina. So they worked together, and this is one of three major efforts from Misha, which got her during her PhD the cover of Scientific American. This is Misha's cat, and the output from her retina. You can show the spatial filtering. And I just want to show you, because I actually retrieved the layout of this recently and looked at it carefully to understand what's going on. So this is done around 1988. It's a scanned hexagonal retina with an HRES surround. That's Carver's horizontal resistor circuit. This is the whole chip here. You see how few bonding pads there are. And you could plug it directly into a monitor and just get the output. Very simple design in some ways. But with no spiking output. It would scan itself out and be presented on a multi-sync monitor. Let me try to explain how this actually works. So you have a photoreceptor here, which is logarithmic, and this transconductor here acts like a conductance. You see the output is connected back to the negative input. So the output current here is proportional to the difference of the voltage, which is this voltage. So this would act like a conductance, driving a current onto this sheet of resistors. And then the output of the retina is actually the difference between this low pass, spatial temporal low pass, and the photoreceptor value. And when Misha showed this high contrast picture of Abraham Lincoln to her chip, this is the output she got. You can see here that in this region here where it's white, and in this region where it's dark, the output from the chip is about the same value, because this value is about the same as this value, as long as you're far away from an edge. But at the edges, it would enhance the output. And that's one of the primary functions of the retina, to extract and emphasize edges in the world, not just flat contrast. But you can also see some of the problems here, right? The mismatch between the pixels. And this has to be a very high contrast thing here. And in particular, one major problem with this thing is, how do you build those resistors? Because real physical resistors on chips are much too low resistance value. You need very high resistances because the currents are very small and the voltages are small. So how do you actually implement these resistors? And the way this is implemented is by this expensive pseudo resistor network. Here again, you have the same circuit, differential output. There's the transconductance. And each resistor is formed by one transistor to the neighboring pixel. And its conductance is set by this transconductance amplifier with an extra diode in this path. That lifts the gate of these transistors above this voltage by the amount set by this bias current, and sets the conductance. So you could tune the conductance just by adjusting this bias current here. But this is expensive. You can imagine in Silicon area, if you actually look at the layout, this is what I did recently. Here's an array of pixels. There's the phototransistor. And all this highlighted stuff here is this pseudo resistor network. These are the transistors here, and these red things here are the polysilicon wires that are connecting to the neighbors. Really expensive. About half the pixel area is just to implement this resistive network. And the actual pixel area that's occupied that's sensitive to light is about 5%. So you're throwing away 95% of the photons right away. They're just thrown away, and you can't afford to do that because you're always photon starved in reality, almost always. But still, this got the cover of Scientific American, and it's a very famous chip. And it was really the first integrated silicon retina. It was very inspirational. But the problems were, it was being developed at the same time as the first CMOS image sensors that you now have in your pocket. But it had huge pixels, a tiny fill factor, terrible pixel matching, and frame-based redundant output. So basically, you just got another frame output that was kind of filtered. Now, you have to realize that all this very minor work in neuromorphic engineering was occurring in the context of the dawn of the CMOS image sensor, or CIS era. And this famous paper from Eric Fossum, the guy you saw before, that appeared in IEEE transactional electron devices in 1997, CMOS image sensors, electronic camera on a chip, really started an explosion of development of electronic cameras that were much better than the CCD cameras of the past generation, because everything could be integrated onto one single chip. And this is a plot here as a function of year, CMOS image sensor pixel size. Starting around 2004, CMOS image sensors already had pixel sizes less than 5 microns, and the pixel size basically shrank linearly up to now by year. And so that means the number of pixels per same chip was increasing quadratically. And so this is called the megapixel race. And this is now a $20 billion a year business every year. So it's a major business, as you can imagine, because everybody in the world practically has a smartphone, right? So all this neuromorphic engineering was occurring in the context of industry that was intensely developing the technology for CMOS cameras. Didn't care about them being redundant, because people just wanted to make pictures and take videos and so on for the most part. And they weren't worried too much about battery lifetime at that point. Okay, so now let's go back to 1992, and I want to show you the very first event camera pixel. And this is from Misha's PhD, and give you some idea of how simple it was and how limited it was to some extent. So you see the pixel here. Here's a phototransistor, a log photoreceptor. So this is a static log photoreceptor. Then you notice this here is a low-pass filter. And then there's a difference between the low-pass filter and the instantaneous value. That forms a first-order GM and C high-pass filter. And then the output current from this high-pass filter was rectified by this current mirror. So you only cared about the negative current, the current being sucked in here. That current being sucked in here when the photoreceptor was higher than the high-pass value was then mirrored into a spiking neuron circuit, which I won't explain here. And this is the response to a flashing LED. And so this had the AR circuits on the edge that turned the events into numbers, addresses, and so on. But this chip was enough to get Misha her PhD, but it was inspirational as the first spiking silicon retina, but it was developed at the same time as these CIS sensors, but it had huge pixels, tiny fill factor, and awful fixed pattern noise. In fact, it was so awful that the only thing Misha could ever get it to respond to, which was sufficient, was this flashing LED. Here's a little video. These are two retinas, each seeing a flashing LED, and that's about all it actually did respond to. And then these flashing LED spikes were matched by the stereo matching chip. If you put a lens on it, it wouldn't respond at all. Then Kameda came along and said, okay, this is too simple. I don't want just a time derivative. I'm going to implement an entire silicon retina with all different classes of cells and so on. And he designed this pixel, which had models of the photoreceptors, the horizontal cells, 4 classes of bipolar cells, and 4 classes of ganglion cells, mimicking the sustained and transient pathways, on and off, sustained, and incrementing and decrementing. And this is all embedded in this very complex log domain pixel. Here's the photo diode. And he could get output from it like this here. Basically, the transient output didn't work at all. These are the on and off events. But he could get output from the other thing. So from this kind of low resolution and quite noisy output, he was able to reconstruct this kind of face video. But it was really limited by transistor mismatch also. It's just the precision was all over the place, and like half the pixels wouldn't respond at all, wouldn't make spikes. And so this is inspirational as the first multimodal retina with spiking output. And the biggest impact of this chip is that Kameda opened all these AR circuits to the entire neuromorphic engineering community, so everybody else could put them on their chip. So that was the real useful impact. But it had giant pixels, tiny fill factor, terrible pixel matching, and no usable computer interface. Okay, so for the people that don't know what transistor mismatch is, what is transistor mismatch? And this is the single one thing that held back neuromorphic engineering over its entire history. The idea that you could build precise transistors. So if you look at the transfer curve of one transistor, here's the gate voltage and here's the drain current on a log scale. This is what it should look like. This is a subthreshold neuromorphic regime of the transistor. And if all transistors acted exactly like that, everything would be different now. But in reality, when you build transistors, the channel here between the source and the drain is implanted with dopant ions that fall on the channel in a random way, like raindrops. And so some transistors might have more dopant ions, some have less, and that causes a variation in the barrier height here. And so if you take a bunch of transistors and actually measure them, these are the curves you get. They vary all over the place. At a particular gate voltage, the current will vary by an order of magnitude between transistors. So that's the one single thing you have to overcome whenever you're building CMOS circuits. So what do you do about that? That became the key question. Okay, so my first attempt to do something about that was in a chip called RETRESET. This is actually quite a cool chip. It used a adaptive photoreceptor, which used a kind of a not switch capacitor, but a capacitor ratio here to amplify the log intensity around its past history. And then this was coupled capacitively into a source follower readout. This is a scan sensor, so you select it row by row and read out the values. And the way it worked was that when this row was selected, you would read out this voltage onto the column. But then when the next row was selected, it would reset this row. It would reset this voltage to a fixed voltage, this V reset. Then by the time the next frame came around, whatever changed here would be stored on this capacitor, it would appear on the capacitor, and you could read out the change in log voltage. Is it clear? Here's a video showing that. This is when my mother, Manny, came to visit the lab. And I said, look, Manny, it was everything in those days. We didn't even do PCBs, we just wire wrap the boards. And you could plug it into the monitor here, nice and simple. It had one bad row here. You see that? That's her blinking. Yeah, so it only sees her when she moves around. It looks like there's nothing in the background, right? Yeah, there's me. Right. And now if you move the camera around, like it would be on an eye that's saccading around, you'll see the background show up too. And so this is actually in Carver's lab at Caltech. So by comparison to everything previously, this is like way cleaner because the matching was much better. And basically, it was a hint to the DVS pixel, this capacitive, the idea of capacitive sensing. This is high contrast response. Yeah, so this is the first scanned high dynamic range retina with a clean output. The output was the change in brightness or log intensity between frames. And the problems of this sensor, where it never had any impact, was it had a sample dense analog output and large pixel compared to CMOS image sensor. Then the lovely man Tetsu Yagi at Osaka University came along. And he is primarily a biologist, but he brought some clever engineer, Kameda, into his lab, and they designed a scan spatial temporal retina, produced this very clean output here. It only had 46 by 40 pixels. It's a very complex pixel that actually implemented 2 HRES networks. And the important thing here is that the input was actually just a CMOS image sensor. You see it's clocked. It would capture a very clean frame here. Then that would drive one resistive network. It would be switch capacitor, drive another resistive network. And then the output would be the change between those 2 resistive networks. Of course, you can see this pixel is very complicated because each of these is not resistors. They're actually that HRES circuit that I showed you before. So the pixel was huge, 180 microns on a side. That means that nowadays you would be able to fit about 30,000 pixels into that pixel, right? Because nowadays the pixels are about 1 micron. So it wasn't very practical for that reason. But it was the first spatial retina to achieve decent matching, but it had an extremely large pixel and a sampled dense analog output again. Then Gerd Cowenbergs and Ralph Etienne Cummings decided to take a shot at this. In 2005, they did the TCTDI, which stands for Temporal Change Threshold Detection Imager. Temporal Change Threshold Detection Imager. I'm not going to try to explain how the pixel works, except to point out that it has only NMOS in it, no PMOS. So it means you don't need a separate end well. That makes the pixel much more compact because the well spacing is the biggest spacing rule. And it had these two little capacitors here to store the sample values from a very simple 3-transistor cis pixel. And from this, they could get rather clean output. So here's Malik, the student who did the bulk of the work. This is the raw intensity output. This is the change output. This is the threshold change output. And this is the rectified change output. And this looks all really nice. The pixel's quite compact. Do you know what the problem is? Anybody have an idea? Yeah, the problem is that it's changed between frames. So if something moves slowly, you get a very small change and it doesn't cross threshold. And also, well, it was the first CMOS image sensor with event output. It had a very small 6-transistor, 2-capacitor NMOS only pixel. And it was the first event camera to put part of the change detection on the periphery. So actually the thresholding is actually on the edge of the chip and it's shared. The problem is that it detects intensity, not log intensity or brightness change. And it has a scanned output and it has very low quality, very low dynamic range 3-transistor APS. You see the problem with detecting, putting a threshold on intensity changes means if you set the intensity change threshold for the bright part of the scene to this value, then in the dark part of the scene, you'll never see any change at all. Because the thing the sensor sees is the product of the illumination and the object reflectance. And what you really want to see is the change in object reflectance or scene reflectance, not intensity. That's what the real retina does. If you do this, you're dead in any high dynamic range scene. Your Kramer realized this, and he did the first cut at an on-off, kind of a DVS, a pre-DVS sensor. The wonderful Jörg Kramer, who died in a heat exhaustion about 2004, actually, right? 2000, yeah, after climbing, a bad water telescope heath in Death Valley. Anyway, he designed a couple of these on-off transient AR retinas. His pixel circuit, I'll try to explain it for the circuits people a little bit. It's not so bad, not as bad as it looks. You'll notice here there's a kind of a log photoreceptor here, but then there's feedback to this log photoreceptor through this very interesting source follower. This is an NFET, and this is a PFET, which is diode connected at the top and bottom. And so what that means is that when this thing completes its feedback loop, the current, this current, required to charge this capacitor C to complete the photoreceptor feedback is mirrored here and thresholded by here to generate events. It means the output events from this sensor represented a derivative of log intensity that exceeded a threshold, a derivative bigger than a threshold. Do you see what the problem with that is? If you move slowly, you don't see anything at all because the derivative is small. Still, Jörg was able to get it to respond to fast, light, high contrast edges. Here is the on channel and the off channel in response to an on edge moving down and an off edge moving down. You see when the on edge moves down, the on channel responds, but the off doesn't. And when an off edge moves down, the off channel responds, but the on edge doesn't. And that happens over quite a wide range of absolute illumination, but it stops working when you get really dark. The big problem with this is it never really worked for real world input. You put a lens on it, and it only responded to high contrast, fast changes. So if you put it on a car and drive around, you basically see almost nothing. And the impact was that it inspired us to do the DVS pixel to solve this problem. So now I'll go through this DVS, which was really quite nice development. And I was lucky to get Patrick Lichtsteiner from physics, not electrical engineering, to join together and develop this DVS, which was developed in the Caviar project, coordinated by Shichi, taken over from Jörg. So the way this thing works, I mean, I'm sure a lot of people are familiar with this, but it has a photodiode, a circuit that turns that into log intensity voltage. And then this log intensity voltage is coupled capacitively to this node here. This node is reset to a fixed voltage every time the pixel generates an event. So what you get is the change of log intensity here. And this is amplified by a rather precise switch capacitor amplifier. So here you get A times the change of log intensity, and this is thresholds to make the to detect the on and off events. And this mimics very loose way the photoreceptors, bipolar cells, and ganglion cells of the retina. It totally disregards horizontal cells and amarin cells, right? For simplicity, because the name of the game is to make the pixel small and simple and accurate, precise. So to explain that a little bit further, the pixel output is then a stream of these brightness change events. And so if you look at it as a function of time here, the log intensity voltage might do something like this. And in response to that, the pixel VDIF node, which is this node here, this is VP here, this VDIF node, it's inverting, so it goes down until it hits a threshold. The pixel generates an event, it gets reset for some refractory period, and so it goes pop, pop on, then it starts going down and it goes pop, 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 off, and so on. Very simple operation, right? I want to point out two things. Remember I mentioned mismatch before? This is probably the key feature that made it work, which is the fact that we put a gain element before these imprecise comparators, because these comparators don't all have the same threshold here. They have a huge variation in the threshold value. But if you refer that back to the input after this gain element, where you remove the DC mismatch, you can push these histograms much closer to the origin. You can squash them right next to the origin, and so you get something with much smaller input-referred mismatch. That's how you can get this rather precise response to small intensity changes. And the other key innovation in this circuit is this really cool 6-transistor, 2-capacitor change detector. I think this is really a beautiful circuit. You'll notice here you have the log photoreceptor, then you have a source follower buffer that just copies the voltage and buffers it. Then you have the C1 and C2 and these transistors over here. So I'll explain how this works in a nutshell. What happens is the gain of this circuit is set by the ratio of these 2 capacitors, and nothing is better matched than that, a capacitor ratio. And when you short this reset switch here, you diode-connect this guy. So this guy settles down so that it sources this bias current here. Then you open the switch, and now you're amplifying any change in voltage here through the voltage gain, the open loop voltage gain of this 2-transistor amplifier. And then you can compare that voltage with these 2 comparators here. This I on is bigger than ID, and this I off is smaller than ID, but the threshold only depends on the ratios of those currents, which is also rather precisely controlled. And we didn't realize this when we designed the pixel, and only realized it later. This also means that the operation and the threshold of this pixel is independent of temperature, because this threshold voltage you get here is proportional to temperature, but so is this voltage here. Everything's proportional to the thermal voltage. So since this gain is proportional to the temperature and this threshold is proportional to the temperature, the threshold is independent of temperature. And that's very important because you don't know if your sensor is going to be used in winter or summer. So you don't want to have to adjust things. So I really do think it's a beautiful circuit. And here is Rafa Berner with some of the DVS 128 cameras we built and sold from Labs. These are some samples from that DVS 128 showing that it responds to these lines. And then Patrick takes his sunglasses off and puts it in front, and it sees the sunglasses, right? It sees the lines right through the sunglasses. Here we recreated the famous milk drop experiment. Because we're recording the events, we can slow it down to 1 kilo frame per second. Here's a spinning coin at regular frame rate. We can slow it down, just play back the events at 500 hertz. And here's the famous spinning dot, was the grinder from Innie's lab, spinning at 16,000 RPM, and we can slow that down to 6,000 frames a second. It even worked under moonlight. This is a true moonlight recording, high contrast target. And you could record slow motion video, like here's Patrick juggling 3 balls. You can slow down and watch sports motion. Or this is Caltech. At Caltech, I recorded the baseball team, the guy pitching the ball. We played around with eye tracking back then. And we did fun stuff like watching cars on the highway and tracking them and counting them. Yeah, you could develop very cheap trackers. And not only that, we could build all kinds of cool robots with it. Like the goalie robot here, there's a camera looking down at the table. You track the balls just like the cars on the table, and then once you know the position and velocity of the ball, you can put the arm to block it. Your Conrad's pencil balancing robot had 2 retinas looking at right angles. A line following robot, we had a retina sitting on the front of the car. A money catching robot, you know, like this game you play in the bar. This is built for a summer school in South America. The slot car robot, you know, the retina is up on the ceiling watching the slot cars. It's controlling one of them. And in this race, it beat lovely Mark Oswald. And the last one I built was this fishing robot. You watch the fish go around and dip down the fish hook at the right moment. Had a lot of fun with this, just pure fun. And these are all handcrafted robots. We never send any of this stuff basically to robotics conferences. No machine learning at all. Basically just handcrafting the feature detectors and the algorithm. Anyhow, this chip had a huge impact because we sold more than 500 of them. And it was really the first production silicon retina with a redundancy reducing brightness change event output, high dynamic range, decent matching, integrated bias generators to provide reliable temperature independent operation, and a USB interface that opened to use to outsiders. But it had problems too. It had big pixels, small fill factor. It was missing a DC pathway completely, and it was very weird to the frame-based computer vision community. They had no idea what to do with it. And so in response to that, you know, you guys all know that biology has, every biological vision system has a sustained and transient visual pathway, starting in the retina, going through the thalamus, and ending up even in the layer 4 of visual cortex, and even you can argue extending all the way through the what and the where pathways. It's kind of this partition that you see all over biological vision. And the transient pathway is faster, coarser, and monochrome, and that's like our DVS. And the sustained pathway is slower, finer, and has color. That's like a CMOS image sensor. So we had to bring that in somehow. Otherwise, we were dead in the water because you only saw one thing, you wouldn't see anything that wasn't moving. And Christoph Posch realized that too, and he developed the ATIS. It's called asynchronous time-based image sensor. Basically, he added grayscale events to the DVS. And he did that by, in his pixel, he had a DVS pixel, and every time the DVS pixel would detect a brightness change event, it would trigger another pixel, which did an exposure measurement by resetting this capacitor high, and then outputting an event when it crossed the first threshold, and then another one when it crossed the second threshold. And in this way, every time you had a change of log intensity, you got a brightness change event, and you also got 2 more events whose time interval would code the absolute intensity. And so we got output like this here, the brightness change events and these intensity events. Where there was no brightness change, you wouldn't get anything. So this is also very weird to the computer vision community, and it had serious drawbacks. It turned out that it had even bigger pixels, it's double the size of a DVS pixel, and smaller fill factor, 3 times the event rate, and very severe motion artifacts. Because in a dark part of the scene, it would take a long time to get these events. So a dark part would measure the brightness much differently than a bright part. You know, it made it very hard to do any real computer vision with it. And so the biggest impact of that is it made us invent the DAVIS. The DAVIS is really a very simple concept. It takes a DVS pixel, and then it tacks onto the log photoreceptor another circuit, which is a CMOS image sensor circuit that periodically resets this capacitor high, lets it decay, and then measures the voltage here at the end of the frame. And the key thing about this DAVIS pixel is it shares exactly the same photodiode. The same photocurrent that drives the DVS also is integrated to measure the intensity. So it's really cool because you can build a DAVIS pixel for about 5 or 10% more area than a DVS. Doesn't cost you anything, and you get the frames as output. And so here's a video I made recently to demonstrate this. It's inspired by Davide's concept video, but this is with a real DAVIS camera of a spinning dot. Showing a spinning dot, and the top are the DAVIS frames. Can you guys see the dot there on the frames? And the bottom are the DVS brightness change events. And if the dot starts moving, you get the same frame over and over again, but no events. But now if the dot starts spinning really fast, all these guys are motion blurred. The dot is severely motion blurred and totally aliased. But you just get a tighter helix of events in space-time. So this DAVIS had a really big impact, I think, because we sold more than 2,000 of them, and they enabled frame event fusion work. But it had a problem too of poor image quality. Basically, the image sensor was only about 50 dB dynamic range and not very high spatial resolution. So it wasn't like the sustained system with finer spatial resolution had the same resolution. So around that same time, we also developed a sensor called CDAVIS. It's the first true hybrid vision sensor, or HVS. That was developed by Changhan. Is Changhan here? No, okay. The idea of this pixel is pretty cool, actually, and it's sort of obvious, but it was quite difficult to actually realize. The idea is here is a pixel layout. You have one white DAVIS pixel that occupies all this purple area, and then around it you have three other pixels, which are red, green, and blue, 4 transistor, global shutter, pin photodiode, active pixel sensor pixels. So these are high performance pin photodiode. Pin photodiode means that the photodiode is buried under the surface of the silicon, so it's very clean. And you can read out the signal with practically no readout noise, no KTC noise. And here's some sample output from that CDAVIS. You can see the color frames. I hope that the rendering here is terrible on this beamer. But anyway, and you can also see the brightness change events. The frames and the events come out at the same time, just like a DAVIS, but now you have real color frames at twice the resolution, VGA, compared to the DVS events. Well, what was the problem with that? The problem with that was that there was no impact, zero. No one noticed that we did this chip. We didn't even notice it. We should have done more to promote this CDAVIS. We were 10 years ahead of industry in this kind of sensor. Okay. Anyway, at this point, industry development really took off, right? So that was about 2014. These are all academic sensors here. And this is the pixel pitch in microns, and this is the year. And you can see now almost all of these developments here are industrial developments. And now, in 2023, the pixel size of these sensors has shrunk down to 2 or 3 microns, which is pretty remarkable considering there were 40 microns back here. Right, so they're about, you can fit about at least 100 times as many pixels in the same chip size. I'm going to give you just a taste of that in the form of 2 industrial developments, so you know what's going on. And you guys all have these in your pocket, right? And they're called backside illuminated and stacked wafer sensors. This is a backside illuminated and stacked wafer DVS, where the sensor is now split into 2 separate wafers that are bonded together. And the top wafer, in this case, is Sony 90 nanometer backside illuminated. That means the light is actually shining down on the backside of a thin wafer. And 40 nanometer CMOS bottom wafer. And this thing had a pitch of 5 microns and about 80% fill factor. 80% of the pixel was active to light. And the schematic of this chip is actually very simple. The top chip just had the photodiode and a couple of NMOS. Then there's a copper-copper bond to the pixel on the bottom wafer and a PMOS. And then the rest of the DVS pixel circuits, about 40 transistors on this bottom CMOS wafer, much finer resolution. And this is done by Samsung and Sony and then Samsung again. So it's kind of a dance between these companies. And the last industrial chip I'm going to show you is now state of the art. Right? This is a complicated slide, but just bear with me because it's quite cool. It actually is triple stacked wafer chip. And it's published at last year's ISSCC from Omnivision, which is one of the big 3 image sensor companies, Sony, Samsung, and Omnivision. And Omnivision and Samsung kind of trade places. Sony's always on the top. But they did a chip, and they wanted to develop what's so-called triple stack technology. The key thing here is that it's a hybrid vision sensor, and in this 4x4 pixel array, which is color pattern, in this Bayer pattern, red, green, and blue, in this repeated way, one of these 16 pixels is a DVS pixel, right? So it's backside illuminated, this top wafer, very thin, and it's 3 wafer stacking. And I'll take you through this here. This top wafer has the micro lenses, the color filter array, the pin photodiode, the active pixel sensor NMOS, and a single copper bump per 16 pixels. So there was one copper bump here connecting this block of 4x4 pixels to the middle wafer. That's how they could fit it, because the pitch of these copper bumps is actually, quite large compared to the transistors. Okay, now you have the middle wafer. The middle wafer has the DVS circuit. You'll recognize it here, right? By now you recognize the two comparators, the change detector, and so on. And it's connected up to this top wafer right here by this copper bump. So the photodiode of this top wafer is connected to the circuit by the copper bump here. It also has a time to digital converter, 4-bit time to digital converter. And it has these so-called through silicon vias that connect the top, the top wafer to the bottom wafer, or the top wafer actually to the bottom wafer. And this through silicon vias are only at the edge of the die, because they're too big to fit in the pixels. And these things look quite cool. They actually drill. These are vias that are drilled all the way through the middle wafer. This is a side view. And you can see all the metal layers and so on. But this is the via that's actually connecting between the top wafer and the bottom wafer. And that's happening at the edge of the chip, and it does all the standard CMOS image sensor stuff, like scanning the columns and rows, and has the, on this bottom wafer, you have the, the column row parallel column A to D converters, and all kind of fancy stuff, you have to have on this industry image sensor now. And the bottom wafer also has the APS readout. It has an event signal processor, which does denoising and stuff like that, and compression of the output. It has an image signal processor that does all the kind of image processing that happens on image sensors. And it has a MIPI, or mobile industry processor interface, that allows this chip to connect to a smartphone, basically. There's no way an academic group can do this stuff. It's just too complicated, and you need too many complex IP blocks. And you also don't have access to this advanced image sensor technology. Yet I want to share with you some of the key specs of this state-of-the-art chip. Altogether, it's 16 megapixel with a pixel pitch of 2 micron. It has a read noise of about 2 electrons. Means the noise on the readout of the image sensor is about 2 electrons, and has a dark current of about 20 electrons per second at 60 degrees. So this is what's expected. It's not particularly great, but it's what's expected now from a CMOS image sensor. And it has very small lag. In other words, very small memory of the past frame. So you don't get trails behind bright objects. The event output from this chip has a bunch of other specs. The total power consumption of the 1 megapixel DVS is maximum about 50 milliwatts. So that's actually pretty good, because when you turn on one of these big image sensors, it's going to burn several hundred milliwatts. It has a very high claimed event readout bandwidth, about 5 giga-events per second. I find this a bit ironic, for a sensor that's supposed to reduce redundancy, that they brag about how many events they can get out, right? It should be actually, we reduce the event, count down, but this is the way they spec this stuff. The key specification I want to draw your attention to is this one, which is the contrast sensitivity, or the nominal contrast threshold, which is about 15%. In other words, you can set the threshold for brightness change to about 15% with a contrast non-uniformity, 1 sigma mismatch between pixels of about 3%. And that ultimately limits how low you can set the threshold before pixels are just firing events all the time. So that's state of the art right now. And Omnivision, Andy Seuss from Omnivision nicely showed me these videos, what they do with this. And you might ask where this is all targeting. What's the big money business now for these companies? It's exactly these expensive cameras, which are basically, the cameras in your phone are the second most expensive chip after the application processor. And so they want to capture part of this market. And what they want to do is improve video quality and low light capability, always. And so one problem they want to deal with is rolling shutter distortion correction. Actually, in these sensors, the shutter rolls across the sensor. That means if something's moving, it gets distorted. People don't like that. And you see the distortion here. You see some of these edges here should be curved, right? These should be straight lines, but they look curved. And by using the events, they can undistort that and make the edges straight again. And they also de-blur. You might notice here, these edges are blurred, but by using the events, they can make them sharp again. And the last thing they showed is this slow motion video using a deep recurrent neural network. They're able to make this 5,000 frame per video, second video of an exploding balloon. It's pretty impressive. You know, whether this is believable in reality, who knows? This is I haven't seen it working with my own eyes. But this is a company that knows how to build good sensors that really work. Okay, so I'm going to end with what we did recently, which is Rui's work. Where's Rui? Yeah, there he is right there, the man. So how does an academic group compete with industry, right? Because the development of a chip like this is probably going to cost about $5 or $10 million in the end. So what can we do? Well, we can work on the pixel architecture and try to explore things that industry won't do because they don't see a market in it. And so what we decided to do was to try to develop a scientific DVS. I don't know, how many people were here for Rui's wonderful PhD presentation? Raise your hand. Yeah, just a few people. Okay, so this is actually seen. So what we wanted to do was develop SciDVS, which is a sensitive, low-light, scientific frame event camera. And the hope is that this camera might be used for applications like calcium imaging, voltage imaging, any applications where the normal, very high, quite granular threshold of a DVS and the high noise at low light intensity just doesn't allow to use the sensor. And so what Rui did was he developed a very cool self-centering preamplifier that he put between the log photoreceptor and the change detector, and he also added a very controllable buffer. So you could low-pass filter the output to reduce the shot noise. And it does make frames. They're not great frames, but at least you can focus the camera with these frames. And it does make very lovely DVS events, which are much more sensitive. You can see the fine details here in Rui's hand, right? So it's more sensitive. And I want to show you the quantitative version of that with this stimulus that Brian and Rui came up with to measure or actually demonstrate that you could see small contrast. And the reason it's hard to see small contrast at low light intensity is that at low light intensity, you got a lot of fluctuation in the number of photons that you get. And if you have a small contrast, and the mean contrast difference might be this, but the fluctuation, remember, is the square root of the number. So they overlap a lot, right? So you have to consider that. So this stimulus is interesting. It actually rotates clockwise in the video. These high contrast edges here reset the pixel. And then these low contrast edges, how many people can see an edge here? I can't see it myself. Can you see a 1% edge? Yeah, that's a 1% edge. This is 1.7% edge. I guess you guys can't see it, right? Can you see this one, 4% edge? Yeah, you can see this 4% edge. Yeah, so it's hard for the human to even see it, right? And if Rui showed you the gray chart, you'd have a hard time, actually seeing that, even if he held it still. And remember, this data that I'm going to show you was captured at a light intensity of about 20 lux shining on the chart. That's less light than I have shining on me here. I have about 100 lux shining on me here, right? So it's 5 times lower than what we have here, so quite dim, actually. So here's that rotating chart, and this white dot here marks the 1.7% contrast. And if you follow this guy, you'll see what the 1.7, you see that SciDVS produces outputs from these high contrast edges. Ignore those. Pay attention to what's happening between this on edge here, where the pixels get brighter, and this off edge here. You see it's responding, at least half the pixels are responding to this 1.7% edge. Yet if you compare it with the Davis 346 that we designed, that Innovation sells, or the Sony Prophecy camera that Prophecy sells, these sensors don't see this low contrast edge at all. So I think the sensor really works, and it has, it's a good potential for it being used in some scientific application. It doesn't have a lot of spatial resolution. It's very clunky right now, but it's good enough to try for stuff. Yeah. That's amazing. I just want to thank, I just want to say some thanks to people. First of all, none of this work would have happened without the fantastic crew here at INI that makes life possible. Katrine and Dave and Simone and Mike and Pavel and Lottie and Ruth. All this work that happened over these decades, and Katrine and Dave were here since the very beginning of INI, have made it possible to do this work in a very painless way. So a big thanks to them. Yes, I'm sure you all agree with that. And all this development, all this event camera stuff wouldn't have happened without the critical funding of 3 European projects, Caviar, See Better, and Visualize. Without the roughly $6 million that these projects came in to pay for all the silicon development, none of this stuff would have happened. And this stuff also wouldn't have happened without the mentoring of Carver and Misha when I was at Carver's lab, without the continual encouragement and support of Rodney and Chichi, and without the initial work of Jörg Kramer. And it also wouldn't have happened if I wasn't so lucky to get Patrick Lichtsteiner as my first PhD student, and Rafa and Christian as probably my second and third ones during this See Better project. And it also wouldn't have happened without the fantastic support and marketing of any labs and innovation of Kainan and Vicente and Luca and Chenghan. I mean, Luca and Kainan are both here, right? Were you guys? Yeah. If it wasn't for you guys, none of this impact would have happened. And also, I want to say thanks to Minhao and Gemma and Diederik, who also did a lot of cool work during, especially the Visualize project and See Better. And finally, the last 2 students who worked on this are Rui and Brian. It's been a pleasure to work with all of them. And thank you.
Where is this stuff all going? Like, because everybody knows that the smartphone is becoming like the PC. You know, they're all basically the same. They don't get better. They add these little features and stuff so people buy them, but basically they're exactly the same phone as last year, right? So what is the next big thing that industry is betting on? What are they betting $500 million per year on? Do you know?
Cameras.
What?
The cameras. Up in
The spectacles. Yeah, just Meta and Snap, the 2 of the world's biggest, well, at least Meta, social media companies, is betting that people are going to buy, instead of phones, they'll also have spectacles, which will be like their brain buddies. They will label you all with your name so I can recognize you. It'll help you repair your car, you know, so they can do this next, or cook your fancy recipe, you know, show some clothes. It'll be your buddy. That's the idea. I don't know if it'll pan out, but they're taking a huge risk on this. And right now, Meta announced that they have their login. Just yesterday, I don't know how many people saw that. Right now, their spectacles cost about $10,000 to build. They have very fancy silicon carbide optics in there. And Snap also, I've seen more of the demo at Sakaya of the Snap demo. It's really impressive, but all of this spectacles is still about a decade away. But they're just not there in terms of the battery lifetime, display, user interface and stuff. But, you know, that may be the next big thing that 1 billion people will buy. So that's where all the bets are going. Right, and then you need an eye, because the eye has to run all day. I don't want to keep you guys for happy hour.
Yeah. So anyway, thanks Tobi again, and
Okay.